Hi, this is ET250, lecture 20. Today we're going to talk about phasors, and phasors are just a very useful mathematical tool to represent AC cosine waveforms. They do require our imaginary number notation, but at the end of the day, they're just a tool. They also allow us to bring our month one steady state analysis tool, KVL, KCL, voltage divider, Ohm's law, current divider, all those tools back into this AC world. It's quite an amazing kind of, I don't know, discovery tool, coincidence, whatever you want to call it. But it's really neat that if we just represent our AC waveforms as phasors, we don't have to learn a new tool set. We don't have to add and subtract with cosines and sines. We can just represent everything as a phasor. Kind of neat. And so what we're going to look at is the assumptions. We're going to remind ourselves that phasors are actually just vectors. We'll look at two forms, polar versus rectangular, and a lot of this should actually be familiar to you. Now in high school, you guys, I'm sure were exposed to imaginary numbers and complex numbers, where the imaginary number j or I equals the square root of -1. We'll go through some examples, and we'll see how do we convert between the two. This will just bring up your basic trig, okay, rectangular to polar and polar to rectangular form. We'll look at how to manipulate them, how do you add them graphically, and we'll go through a full example using them. And then as a little bonus, we'll plot this example in Excel and then look how can we use the TI-89 to make our lives a little bit faster, okay? All right, let's begin. So phasors. Phasors are just, like I said, a compact way to represent sinusoidal signals in a vector form. So here's an example sinusoidal signal. We've seen this before. IP is the amplitude, omega is the angular frequency, and theta is the phase that shifts it left and right. Okay, T is just the unrelenting time that keeps going on. Okay, now there's 5 terms you can see here. There's IP, right? That's the amplitude. There's the cosine. This tells us whether respect to the starting time, is it peak versus sine, or is it 0? Like if it's a sine of 0, it's 0. If it's cosine of 0, it's 1, right? You have the angular frequency. That's the squishiness on the horizontal. You have time, and then you have phase, which is how it shifts left and right. And this could be degrees or radians. Okay, well, we are going to assume when we are dealing with phasors and we have different phasors and different signals that you are always going to use cosine, and all the signals have the same frequency. That's key. We're not mixing different frequencies, and all signals share the same time, right? So that means 0 time for one signal is the same as 0 time for the other signal. Okay, so that means these 3 things are going to be the same when we're dealing with multiple phasors, multiple signals. However, the amplitude and the phase could vary. And so we can represent the phasor version of this guy here as just the amplitude. And then we use this angle notation. So it's just literally an angle. And then we put the phase angle in here. And you can kind of see this is why they call them phasors, because they really look at that phase angle. And notice I have I peak, right? And what I'm going to do, and I expect everyone to do it, is put A peak or AP for the unit. So not just amps, but amps peak, and if it's volts, volts peak. Now, the reason why I want to put this distinguishing character, peak or P, is because you can also use RMS. You just have to be consistent. So you could have quoted the phasor as RMS theta I. And remember, RMS is the root 2 of this, right? IP over root 2 is IRMS, okay? And so here you would want to write RMS in your unit, okay? So, like I said, the intuition for a phasor is that phasors are just vectors. Phasors are just vectors. And recall, if we have a vector, now this should go right back to your statics kind of classes, we can represent in 2 ways. And how do we do that? Magnitude and direction. And what we call this in the phasor world as polar, right? Magnitude, which is the length, and the direction, theta v, okay? So how would we write this? Let's be very precise, mathematically precise right now. You have a vector v, and we put a little hat to denote that it's a vector. And it has an angle, theta v, and a length. And how do you denote the length? Well, you take that v and you put these like either single or double bars here, right? So you have your single or double bars. When you do that, what is that saying? That's the length or the magnitude or the amplitude of that vector, if that makes sense. Okay, so this is your magnitude and direction, your polar form. Should be a review here, no problem. What's the other way to represent the vector? It's in your Cartesian components, or what we call in the streets rectangular. Okay, so your rectangular form, what do we have? It's the x and y component of your vector. So v is vx in the x direction plus vy in the y direction. Okay, so this is your rectangular form. Now, for phasor plots, we are not going to just plot it on the x hat and y hat plot. We're going to plot it on the complex plane. We're going to use the real and imaginary. And instead of the axes, instead of x hat and y hat, we are going to use the real axis and the imaginary axis. Now, there's some videos that describe it, an imaginary number, and I'll probably put some links into the description. Check it out. But imaginary is probably the worst name possible for they should have called it lateral. That would have been a much better name, because the imaginary implies that it doesn't actually exist. And so I really hope, because we'll talk about imaginary power later on. Imaginary power is not imaginary as in doesn't exist. It definitely exists. So if you can try to get rid of the idea that imaginary is kind of fake, that would be good. Okay, so it's the same idea. So let's say you have a phasor now, okay? And like I said, phasors are just vectors, and we can still have an angle and a length. And so the length is that IP that we saw. So that IP is right here. Okay, and the phase is just this phase, no problem. And you can see that we have a real and an imaginary part. That's like the Vx and the Vy here, the X and Y coordinates, right? And so if you want to represent it in polar form, which is this, then you have this version. This is a polar form version of the phasor. Okay, now if I want to represent it in rectangular form, I would take the real part of I and the imaginary part of I. Okay, now here's the difference. Look at this. Notice in here I have x hat and y hat. When I write it in rectangular form with a complex plane, I actually have a reduction in notation. I just have nothing for the x hat, and I put a j here to tell me that this is going to be in the y axis, right? And remember, the imaginary number is j, or defined as the square root of -1. Okay? Okay, good, good. So let's keep going. So let's kind of revisit. If you don't remember your imaginary numbers or all the rules, this is the definition. And you can imagine if we take the j and multiply it by itself, we get -1. So j squared is -1. And like I said, it denotes the y-axis. And here's a very useful property. If you have j on the bottom in the denominator, then if you want to bring it to the numerator, all you got to do is make a negative. That's kind of nice, right? Because you might see this as j on the bottom. You're like, what does that mean? Well, if you just put j on the top, and change the sign, that's all it is. And so here's a simple proof. If you have 1 over j, which is the same as 1 over square root of -1, I can multiply the top and bottom by the square root of -1. That's just 1. And what do I get? I get a j on the top, and I get -1 on the bottom, which is -j. No problem there. So just a useful fact that is going to be helpful later. All right, let's keep going. So now let's take what we just learned and apply it to sinusoids. So let's say we have two sinusoids, V1 and V2, okay? And what do we notice about these two sinusoids? Well, we notice that this sinusoid isn't phase shifted left or right, but we see that this V2 is phase shifted. It's lagging by about 170 degrees, right? Can you see that? So if it was 180 degrees, this peak would be right over this point, but it's about 170 degrees, right? So V2 lags V1. So if we were to plot these two on a complex plane as phasors, you can see V1 would point it in the 0 degree, yep, and V2 would be plotted in the clockwise direction here, right? Okay, so what does that mean? That means that V1 is leading V2. So what happens here? If I have something that is more clockwise then it is lagging. If I have something that is more counterclockwise, then it is leading, okay? So you can see that V1 is more counterclockwise by about 170 degrees here, which is corresponding to our oscilloscope time plot, right? V1, you can, and these are equivalent statements. V1 leads by 170 or V2 lags by 170. Those are the same behavior that's going on. The other thing I want you to note is the amplitude. So on a phasor plot, you can see that I can see the relative amplitude of both of these signals. V1 is this length, V2 is a bigger amplitude, it's a longer length, okay? So instead of plotting these sinusoids, right, with all these lines and everything, what you can do is you can plot all of them on a phasor plot, and you can immediately see which one's leading, lagging, which one has a bigger amplitude. So again, this is more of the simplicity of what phasors bring to the table. Okay, let's keep going. So now let's take an example. Let's take a sinusoidal signal and convert it into phasor, and let's see what we got going on. Okay, so we can provide the phasor in peak or RMS, you remember that? And we can plot, let's plot on the complex plane, all right? Okay, so for this one, we can write this phasor as a peak phasor, where we just straight up take the 15 and straight up take the negative 45, and again, we put amps peak. Or we can write it as the RMS version, where we have the 15 over root 2, but we still have the same phase, negative 45, negative 45, okay? This is a 15 over root 2 is 10.6, and that's good. That makes sense. 10.6 is smaller than 15, right? And if we were to plot this, this would plot like this. So this sinusoidal signal on right here would be represented as a phasor pointing down by 45 degrees with an amplitude of 15. And we put an amps peak just to denote we're using the peak version. Good. Okay. Now, how would you convert, by the way, if you were, this is polar form, how would you convert between rectangular and polar and rectangular, right? And I hope you see it's actually not too bad. So we have our vector, we have our phasor, right? We have the length and the angle, or the real part and the imaginary part. Well, if you knew these, you would just get I by the Pythagorean Theorem, basic trig geometry, right? So you would take the real part of this I squared plus the imaginary part of this I squared square root, and you get I, okay? Now, one thing that a lot of students make a mistake is they put the J in there, and then that messes things up because they go, well, I got a J here, and you got J squared, and that becomes -1, so you get this squared minus this. No. You don't want to have the J in here. You actually remove the J out of there, okay? Okay, now what if you know these two, imaginary and real, and you want to find the angle? Well, how could you find it? Well, you can use tangent. Tangent of this angle equals the opposite over adjacent. So that means if you knew these two, then this angle equals the inverse tangent of the imaginary over the real, or the opposite over the adjacent, right? So that's the solution. Cool. Okay, now A tan is tan inverse. Okay, no problem. So if you see A tan, you see tan inverse, same thing. And again, the same thing. When you're putting these numbers, you don't put the J in here. The J is just the placeholder to tell you it's in the y-axis. All right, let's keep going. Okay, now let's say we want to go the other way. Let's say we have I and theta, and now we want to find the real part over the imaginary part. Well, if I know this length and this theta, well, the real part is going to be the cosine. Remember that? Cosine is adjacent over hypotenuse. Cosine of that angle is this over this, right? Okay, so cosine is adjacent over hypotenuse. So it's the real part of the hypotenuse. So that means the real part is going to be this length times the cosine of that angle. This is going to come up over and over, ladies and gentlemen. So please make sure you got that one memorized. What about the imaginary part? Well, we use the sine, okay? The sine is opposite over hypotenuse, so that means that we get this. And, okay, imaginary part of I is the length times the sine of that angle. I mean, a lot of this stuff, yeah, I'm going a little fast, but we should, you should just be able to eat this up, right? This is all stuff we've seen before, especially in statics, right? Okay. Now let's do some phasor manipulation, right? Which is just vector manipulation. Again, this is stuff you've done before, right? For addition and subtraction, it is easier to use rectangular form, right? Go back to your statics. When you have your forces in different directions, what did you do to add them up? You brought them into Cartesian form, you added up their components in the X and Y direction, and then if you wanted to, you could bring it back into polar form, right? Now for multiplication division, you can straight up use polar form. That is nice. Okay. So what are the rules? Well, like I said, for rectangular form, you just add and subtract the components. So if you have I1 and I2 like this, and you want to add or subtract, easy, right? Let's say we want I3, which is just I1 plus I2. Oh, that's straightforward. 3 plus 7, 4 plus 6, I'm going to get 10 plus 10j. No problem. I want to subtract I4, let's say I1 minus I2, 3 minus 7, 4 minus 6, all in their components. Easy, negative 4 minus 2j. Okay, no problem there. Now, what if you want to multiply and divide? Well, you got some interesting rules, but as long as you remember the rules, it makes everything easy. Okay, so if you want to multiply, you're going to multiply, and you're in polar form, you multiply the magnitude, but you add the phase. If you want to divide, you divide the magnitude and you subtract the phase. So for example, if you had two phasors, A and B, 227, 3 angle 30, and I wanted to multiply them, right? I would multiply the magnitude, which is 6, but I would add the phase, which is 30. That's it. If I want to divide them, then I would divide this and I would subtract the phase. So I would get A over B, 2/3 and 27 minus 30, right? Because B is in the denominator. And I get 2/3 and 24 degrees. That's kind of nice, right? Very simple rules to add and subtract, multiply and divide. But if you want to multiply and divide, it's much easier in polar form. And if you want to add and subtract, it's much easier in rectangular form. Okay, now sometimes there's exceptions to the rules, and sometimes it's easier to add and subtract graphically. So let's say you're given in polar form, right? You have it this, but you want to add and subtract. Well, if you want to add and subtract, yes, you could convert all these to the rectangular form, but maybe you just want to visualize it first, okay? And so let's try it graphically. So what does that look like? Well, it looks like this. I1 is 4 with an angle of 0. And I2 is 4, but with an angle of 90 degrees. Is that right? Well, we can add that. So if I bring this, the tail over here to the head, I'm going to get a vector that's pointed like so, okay? Like this. And we recognize this as a simple 45 triangle. And we know that this length is a root 2 of these ones. So 4 root 2 angle 45. Okay. If you did this, if you converted this to the rectangular form, added their components, and then converted back to their polar form, you'd get the same answer. Okay, let's look at a full example. So let's say we have two signals, I1, I2, and I have 2.7 cosine of 377t plus 72, and I2 is 5.8 cosine of 377t minus 45 degrees. Okay. And let's say I wanted to find I3 equals I2 minus I1. Now I can do it this kind of crazy way. What can I do? I can go in and I can use some trig identities, and I can rejigger everything and use another trig identity, and then crunchy, and I would get finally I3. Gross, right? Or I can remember, well, what if I just represent these two guys as phasors and then just subtract phasors? That might be easier, or at least easier to think about. So if I use phasors, I1 is just this, 2.7 angle of 72. And I2 is 5.8 angle of negative 45. Okay. And I just want to subtract it. Well, this might be hard to get graphically, but we can try. We can just, at least we can visualize it graphically. We might not be able to get exact answers, but we might really at least get a ballpark, get some intuition. Okay, so what would this look like? So let's plot the 2.772. That's going to be plotting up, and the 5.8 negative 45. That's going to be pointing down. So we have something like this: I1 and I2. Okay, this is a smaller amplitude. This is a bigger amplitude. Okay, and so what do we see here? We can see, well, maybe this is too much. I'm just going to draw it here. I'm going to draw it here just so that it's a little bit less crazy. So this is I1, and let's see, this is 72 degrees. Yep. And this here is I2, which is minus 45 degrees. Longer length, longer than this one. Okay. So now we want to take, let's say we want I3 equals I2 minus I1. Well, I1 is positive this way, or negative I1 is that way, right? Okay, when I combine vectors, instead of subtracting, I like to just add vectors. So I like to go I3 equals I2 plus negative I1. It just makes it easy for me. I don't know. And so here I take this I1 and then I can say, well, this I1 is, or negative I1 is this one, right? So this is my new I3, right? Because add this vector to this vector, if that makes sense. So we can see that I3 is going to have some angle which is going to be bigger than 45. So maybe negative 60. And this length is going to be bigger than 5.8 even, right? Because look, it's a little bit longer. So I don't know, maybe 6.5, something like that, right? So this would be our new I3, which means if we were to write it out here, we would say I3 of t is equal to 6.5 cosine of 377t minus 60 degrees, right? And that would essentially be what this is. Look at this. I mean, I know I'm not getting exact numbers, but at least I'm getting a graphical feeling pretty quickly, right? Okay. Instead of having to crunch everything, I at least have a sense of what it's going to look like, right? Which means if I were to plot I1, what would I1 look like? I1 is, let's see, plus 72. That's something that's positive phase. So it's shifted a little earlier in time. So this would be I1. What would this be? This would be I2, something shifted a little bit back in phase. So that's something like with a bigger amplitude. Well, that's like this, right? And then what is I3? I3 is even bigger and shifted a little bit more. So that's something like this. So this would be I3. So already, without doing any math, I'm already picturing what I3 is looking like, what I1 looks like, what I2 looks like, what I3 looks like on a time plot. And we already have a sense of what I1, I2, and I3 look like on a phasor plot. Haven't done any math yet, really, right? Okay, so now let's apply what we just learned and start crunching everything. Okay, so let's see what we got. We have I1 and I2. And if we want to subtract, what did we say? We probably want to use rectangular, right? And if we want to use rectangular, and if we know the length, and if we know the angle, we can use what? The length times the cosine of the angle and the length times the sine of the angle to get the real and imaginary parts, right? Length times the cosine to get the real part, length times the sine to get the imaginary part. Okay, so that means I1 has the length times the cosine of that angle plus the length times the sine of this angle, right? And if you always forget how to do this, just go back to your phasor plot. Look at I1, right? If I know this length is 2.7, I want this real part here. Well, yeah, that makes sense. I would take this length times the cosine of this angle right here. And if I want this length, or this length here, I want this length times the sine of this angle. And that's these two numbers. It's the same thing for I2, right? It's the length times the cosine, the length times the sine. And notice I put a little j, 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 j. Do these numbers make sense? 0.8, 2.5. Okay, what about this? 4.1, negative 4.1. Yeah, because that was a 45 degree. So when you get the numbers, you want to make sure these are making sense. Good. All right, I3 is just easy because I'm just subtracting. And now because it's in rectangular, I just do point to point. 4.1 minus this, negative 4.1 minus that. Okay. And so I get 3.27 and then minus 6.68, right? Okay, so if this is 4, good. This is like, let's say 4 and 4. Now this is 3.7, but minus 6. All right, I think that seems to make sense. Good. And now, once I have this, I can now convert it back to polar form. So now if I have 3 and I have 6, I just get the length. So that's Pythagorean theorem. And if I have 3 points and then negative 6, I want to get the angle. I just can use the tangent, right? All right, so let's do that. So good. The, what do you call it? Pythagorean theorem, and then the inverse tangent that we just talked about. Punch them into the calculator. I3 is this. Theta is inverse tangent of this part over this part, and we're good. Now be very careful. Look what I did or didn't do when I did this computation. So I have 3.27, and I put plus negative 6.7 squared. Did I put a j? No j. No j. Let me even write that in here. No j. And then same with here, no J, right? I don't know, no J, I don't know, can I put a quotations, exclamation? Yes, no J, all right? Don't make that mistake. Okay, good. And then I get my numbers, 7.43 and negative 63. Oh, that's nice. That's kind of roughly close to what I predicted, right? 7.43, at least it's bigger than 5.8 and negative 63. And this is my I3. So, yep, something 7.3 cosine 377t minus 63.9 amps, okay? All right, not too bad. And then look here, my phasor put amps peak. Here in my cosine version, I don't have to define amps peak or amps, because when you write it like this, as time varies, you're neither at amps peak or RMS, right? So maybe I'll write that here, is like, don't put amps peak or amps RMS, right? When you're writing it in this cosine form. When in cosine form. Okay. All right. So what I want to do now is I want to go to the computer and see this in Excel. So let's remember what we have here. We have 2.7 amplitude with a positive 72-degree phase for I1. We have 5.8 amplitude with a negative 45 for I2. And we have 7.43 with a negative 63.9 degree for I3, okay? And we are taking I3 from the subtraction of I2 minus I1. Notice all three have the same cosine, they have the same angular frequency and the same time, matching the assumptions of the first page. Okay, so let me go to the Excel. So go here and let's do this. All right, so if we look at Excel, what I have here plotted is I have the same angular frequency for I1 and I2. I have the, what do I have? I have, let's see, let's make sure I'm on the right page here. Okay, I have the same time for both, good. And I have I1 as the cosine of the angular velocity here. So if I click this, you can see how it's calculating. Angular velocity times time, which is the A column, plus the phase, which is here in radians. Notice I made sure it's all in the radians, even though I put in 72. And I have it times the amplitude, which is B5. Good. And I just propagated that all down. Okay. If I look at I2, it's the same thing, except it's using the I2 column. Same frequency, time. It's the corresponding radian of the negative 45-degree phase and the amplitude of 5.8. Okay. And look at I3. I3 is just the difference of I2 minus I1. And what did we do here? We have I1 in blue. We have I2 in orange, and notice I2 is a bigger amplitude, good, and it's shifted to the right. It's lagging because it has a smaller phase. And look at I3. As we predicted, it has an amplitude that is bigger than both of these, and it's shifted even more, right? It's shifted by about whatever 63 degrees. So I hope this this plot convinces us that by doing that simple math, it's all good. The last thing I wanted to show you was a TI-89. Like, how could you do this on TI-89, right? Instead of doing even all the rectangular form and all the, what do you call it, Pythagorean theorem and inverse tangent, can the TI-89 just do it for you? So let's check this out. We got our online simulator of the TI-89. Now, here's a few things you want to make sure. You want to make sure you're in the correct mode. So you see how I'm in radian mode here? Well, maybe you want to be in degree mode. It's pretty easy. Just go to mode, and we can go in here and go click, 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 and just set it to degrees. So we'll go 2 and enter. And now here's the other cool thing. I can do my phasor. So what do we have? We had I2 minus I1. So I2 is 5.8. So watch this. 5.8. Notice I put the parenthesis, and I can do this angle. See the sneaky little angle? I got to hit second and angle. And then I can put the angle of negative 45. Negative here, not this minus, but negative 45, and I can close it off. So that's I2. And I can go minus I1, right? Well, what's I1? 2.7. So I got a parenthesis, 2.7 with an angle of what? 72 degrees. Boom, boom. And I can hit enter. And look at that. It gives me the answer, 3.2 and minus 6.6. And it even gives me a little eye. That's kind of cool. That's our rectangular form, right? So let's say I didn't want it rectangular form. I actually want it in polar form. Well, I could go to my mode here and I could say, well, instead of polar form, can I please have it in, or instead of rectangular, can I please have it in polar form? So I go to this complex format and I can go, please give it to me in polar form, enter. Okay, so now I'm in polar form, enter again. And if I hit enter on this, oh my God, check it out. 7.42 with an angle of minus 63 degrees because I'm in the degree mode. Man, no inverse tangents, no Pythagorean theorem, no cosine, no sine. Your TI-89 does it all for you, ladies and gentlemen. This is fantastic stuff. Okay, and so you can convert back and forth. It's super nice, right? Use this, please, right? I think it just makes things a lot easier, and make sure you have the intuition. Okay, well, I hope this lecture helped, and yeah, I'll see you in class.